So our position is getting less and less significant. Very bizarre, very surprising. That's the way it is. I'm now really beginning to get to the final phase of all this, beginning to face these questions. And the big questions seem to be, one, how did all the antimatter go and how did there be an excess of matter left out of it all? Secondly, how did it come about that we started with this uniformity in the Big Bang and ended up with galaxies of stars randomly distributed around the sky? And the third real question is, and how did all this mass come about anyway? I mean, according to all our theories and equations, when the universe began, everything would be flitting around at the speed of light with no mass at all. Now, these are three big questions that we're trying to get to grips with. And surprising as it might sound, there appears to be a common thread to them. And now I want to sort of move towards these frontiers that currently are beginning to attract our attention and see where they lead. So, the common thread seems to be this. We started off with a hot Big Bang where everything was uniform, very high energy. And now we have ended up with a cold universe, highly structured and lopsided. How did it come about? You went from this uniformity to this lopsidedness. What triggered that thing? Well, it turns out that this change from uniformity to lopsidedness is much more common than you might realize. We've got some demonstrations of the disappearance of symmetry and the appearance of asymmetry, as it's called, here in the room. Now, the first thing I need is a volunteer who is highly symmetrical. Are you a highly symmetrical volunteer? Yes, okay. What's your name? Catherine. What I want you to do is to stand on that cross, which has been prepared very accurately, and be as symmetrical as you can, and Bryson is going to bring on the apparatus. Right, so you are positioned symmetrically exactly halfway between two identical bars of chocolate. Now, what I want you to do when I say go, you can choose either one of those and pick it up, okay? Great, well done. I think you did so well, you can keep that. Thank you very much. Look what we've got. We started off with this completely symmetrical beginning, and then by some random choice, asymmetry. So that's a simple example of asymmetry out of symmetry. Now let's take a second example of going from a high energy state to a low energy state and seeing how the universe might change. So this is the next of our demonstration. And for this, I've got three of our volunteers here. In fact, these are three of the ladies who've been helping Bryson and his team make many of these demonstrations. So if this one doesn't work, it's their fault. Right, okay, Zoe. What we've got down here is an empty drink can, which Zoe is going to stand on and balance, and Karen and Jessica are just going to help support her balance, okay? So we see the drink can supports her whole weight. Righty-ho. Get the whole of your weight on there, and I will introduce a bit of asymmetry. There we go. Thanks very much. So we started off with that very highly ordered drink can, just like the highly ordered early universe. A little bit of asymmetry was introduced, and now you're left with this. This is the universe today. There's no way you would reconstruct the original drink can out of this. Something made the change. So that is the sort of idea we have. Let me give you an example from the real universe. Here, I'm taking a drink of a well-known substance, water. Nice and warm. The molecules in it whizzing around in all directions, complete uniformity and symmetry. Freeze it. You have the snowflake. Beautiful structure, highly ordered, but no longer the total uniformity. a clear structured system. You've gone from the liquid state where it's warm, high energy, to the frozen state, and you've got structure. That is the sort of idea we think is going on in the early universe. So, what we've done, we've gone from hot, like the drinking water, to the frozen cold, like the present universe with structure. The question is, what introduced that asymmetry? What triggered that change of phase, as we call it, from the liquid to the frozen structure that we see today? Now, there's many ideas about, and this is really one of the hot topics at the moment. And among the front runners is an idea due to this gentleman, Peter Higgs. Now, Peter Higgs is Professor of Theoretical Physics at Edinburgh University, and his theory is the one that is currently the front runner and that everybody is trying to get to grips with. And to summarize it in 4 lines, there it is. I don't need to say any more. Well, yes, I do. I mean, I must stress here that now we're really at the cutting edge of science. We're getting to the point where we are trying to understand these ideas, which are really only yet being formed. But let me see what we can do. Here we have got a model of the universe. At the start of time, we've got 2 identical particles. Now, when the symmetry broke, it could have gone the red way or the blue way. Some, we don't know why, but some particles feel the red route and just go happily straight down, sort of flighty, fast, moving like the speed of light. Other particles, however, feel they get gripped, they get slowed down. There's an inertia about them. They sort of get weighty and heavy. They've gained a mass. Let's sort of show this again. Some things don't seem to care, and other things get gripped by some force, the Higgs force, a 5th force in nature. Now, this idea of a 5th force in nature is something quite new. In fact, even in my own books, I say 4: gravity, electromagnetic, the weak and the strong. Now, if Higgs is right, there's a 5th force about, and it was this that triggered this change. Now, this is so exciting, people, that almost all the theoretical particle physicists in the world are currently trying to understand this, devise tests of it, and do experiments to see if it's right. And it's been so interesting to people that even our science minister, Mr. Waldegrave, decided that he would like to know much more about it. And he issued a challenge earlier this year to the scientists to say, could we describe to him the idea of this Higgs force on a single sheet of paper? And he offered prizes of bottles of champagne for the best solutions. Now, I was one of the many entries, and I was a little bit worried about this, because there's this famous case that Richard Feynman, a well-known physicist from the past, just after winning his Nobel Prize, was asked by an enthusiastic reporter, could he describe his Nobel Prize in 30 seconds? And he said, if I could describe my Nobel Prize in 30 seconds, it wouldn't have been worth the Nobel Prize. So I was a little bit worried about the idea of being asked to describe these very complicated ideas on a single sheet of paper. But I said, I'll be happy to try to do that if in return you will do the same on behalf of the Maastricht Treaty.